Hello everyone, I'm Karol, and this is the presentation about dynamic longest common substring in polylogarithmic time, joint work with Panos and Paweł. Let me start with a few definitions. So a string is obviously a sequence of letters from some fixed alphabet of size sigma. We will denote strings with capital letters, and of course we can concatenate strings. And a substring of S is basically any slice of S from some position to some position. It should be consecutive fragment of S. And the problem of LCS, longest common substring problem, is as follows. We are given two strings, S and T, each of length at most n, and the goal is to find the longest string, that is a substring of both S and T. So in this example we want to find the red string. And around 1960, Knut conjectured that this problem requires n log n time. This conjecture was later refuted by Weiner, who presented linear time solution in quite famous work that introduced the suffix tree. And I would like to stress that we should not confuse this problem with longest common subsequence, which also is like LCS problem. And this is a completely different story. And whenever I say LCS, I mean longest common substring problem in this presentation. So what was known about the LCS problem? So there is a space-time trade-off for t, for any parameter t between 1 and n. It's possible to construct n squared divided by t time algorithm that works in t space. There were many papers on approximate LCS problem, for example, under Hamming or edit distance. But what we considered is we considered fully dynamic LCS problem. So we are given two strings as earlier, and now we are allowed to perform letter substitution. We want to maintain some data structure that helps us in answering LCS queries in dynamic strings. We can choose any letter, either in R, in S or T, any position of string, and replace the letter here. And we want to still know what is the LCS after such update. So we can replace the letter, and potentially the LCS is now completely somewhere else. And we can replace the letter in another string, and the LCS can be completely different place again. So there's also another variant, which we call partially dynamic LCS, in which only one string is dynamic and another one is static. So this line of research is not new. There were many other text problems, string problems that are created in dynamic fashion. So, for example, pattern matching queries for dynamic text, maintaining repetitions in a dynamic text, for example, squares, Lindon decompositions, longest palindromic substring in dynamic string, and so on. There are many other problems. We considered dynamic LCS problem. And what was known about this earlier? So for partially dynamic LCS, so this variant with only one dynamic string and another static string, we had update time. Earlier there was paper that had update time root of n times several logs, and space was bounded with n polylog n. So this O tilde notation will hide the polylog n factors. What we did in our paper is we reduced the update time to log square of n. And if we are allowed to use a little more space, like n to 1 plus epsilon, it's possible to get the time even further down to log n. And we also showed the lower bound, so it's not possible to construct an algorithm that works faster than log n over log n if the space is n polylog n for partially dynamic LCS. For fully dynamic LCS, so both strings are dynamic now, the update time was known earlier to be n to 2/3 times several logs, still with n polylog n space. We were able to get this down to polylog n, We are not counting logs now, but this constant is around 10 or maybe slightly less. We don't count this. Hopefully you don't count this too. Thank you. And there's still upper bound, there's still lower bound, and actually even slightly stronger lower bound. Even for polynomial of n space, any power of n, any constant power of n space, still the update time lower bound log n over log n holds. So let me first tell you how the algorithm for partially dynamic LCS works. Later we will move on to fully dynamic LCS. We will not speak on lower bounds in this presentation. Let's assume that for partially dynamic LCS, S is the dynamic string and T will be the static string. The idea now is to decompose S into several blocks. So each block should appear somewhere in T. Yes, we decompose S, but each block should appear in T. But the concatenation of two consecutive blocks is not appearing in T. So that's the idea, and if we maintain such decomposition, we have a very nice property that any common substring of S and T is contained only in at most 3 consecutive blocks. This is quite obvious because if it would be 4 or more blocks, then such substring would contain at least 2 full blocks of the decomposition, and 2 full blocks cannot appear in T by definition. So how to update such structures, how to update such decomposition? So first we have to locate the block with the position that we want to update. This is easy if we have some predecessor data structure. And then we split the block into 3 blocks, the prefix of the block and the block that contains only the updated letter and the suffix. We just update the letter, and later we have to merge the blocks. This is done greedily, and only local. This is only local operation. Only few blocks to the left and to the right of the updated letter needs to be considered and potentially merged. And checking if we can merge 2 blocks if they appear in T is easy if we do the proper preprocessing of T. And because of this locality, only constant number of block operations are needed for each update. And how this block decomposition helps. So basically now to find any common substring of S and T, we focus on block boundaries and we treat each block boundary as an anchor to our common substring. And any common substring can go from this anchor only at most 2 blocks to the left and 2 blocks to the right. Actually, it won't be 2 full blocks, but at most a block and some part of another block. So only constant number of blocks needs to be considered to the left and to the right. So what we can do is we can have some data structure that for each anchor stores pairs of strings, the string that goes to the left from the anchor and to the right. And we can store these pairs of strings in some data structure, and these are some trees, and what we can do is we can reduce the problem to so-called heaviest induced ancestor queries on suffix trees of T and suffix tree of reversed T. I will speak on this later, so hopefully it will be more clear in a moment. But the general idea now is for each anchor generates a chunk, like 2 blocks to the left and 2 blocks to the right. In each such chunk, we can find LCS between such chunk and T. Each such chunk reports the result to some max heap of candidates. This is some predecessor data structure. And only constant number of chunks are updated if the block is updated. Yes, so this is This is how we can maintain the best result. So when we want to solve the fully dynamic LCS problem, when also T is subject to change, it's not so easy because the block decomposition can change completely after just one update of a letter in T. So instead of having just one decomposition, we have a hierarchy of decompositions. And so we have hierarchy of decomposition for S and hierarchy of decompositions for T. So now we have two structures, both for S and T. And the idea is a little similar to the previous one. So for any common substring, we want to be able to find some level of granularity in our hierarchy of decompositions, where X appears and it crosses the boundary of blocks. So still we want to be able to find some proper anchor from which we can go just few blocks to the left and few blocks to the right, and our full substring will be contained in there. Of course, we want to create such structure in a way that each letter substitution produces only few changes in the decomposition. Yes, so that's the idea. And to achieve this, we use the idea of locally consistent parsing. So this was known earlier. This is not a new idea, but we just use the variant that appeared in Soda 18 paper. So let me first tell you what is this locally consistent parsing. For both words separately, for S and T, we want to represent the word as a context-free grammar that generates the word. So we want to create a context-free grammar which produces only that one word. So there will be just two types of rules in our context-free grammar. Either concatenations of two non-terminals or power of non-terminal. So how this context-free grammar is created? We start with our word, and we first get rid of runs. So run is a sequence of consecutive letters which are the same. So we create non-terminal for this and proper production rule. And the same runs should get the same symbol in our grammar. And later is we perform half compress. So we split the non-terminals into left and right part. We have the alphabet of symbols in our grammar. We split this into left and right symbols randomly. And now, if we have occurrence of consecutive left and right symbols, so there is a left symbol that immediately precedes right symbol, we create a rule, a concatenation rule for this. Yes, so, and of course the same rule is applied for the same non-terminals, like CA in our figure appears twice, and this is both expressed with E that produces CA. And we continue this process further up. So this will create a context-free grammar, and this generates only this one word. So now the nice property of this is that height of this parsing is only log n with high probability. This is quite easy to see because each run compress gets rid of runs. So when we perform half compress, we have a sequence of symbols, and no two adjacent symbols are the same. So when we randomly split into left and right part, if we split the alphabet into left and right part, there are 4 cases for any pair of adjacent nodes, either left left, left right, right left, or right right. And in one of these 4 cases we create a compression rule for this. So basically the expected length of word is decreased by 1/4 every two compressions, like run, compress and half compress. So the height of the tree is log n with high probability. And what is nice about this parsing is this parsing gives us ability to find context insensitive decompositions. So for any substring of string for which we build the parsing, for any substring, even if it appears multiple times, it is produced by the same symbols in our grammar. This is a little bit technical. Either it's the same, or sometimes there is some small. It may be some small difference on the borders of this, but let me don't get into these details. So for each substring we can construct this up layer and down layer. Basically this is up layer, this A, E, I is up layer here, and A is down layer. So we can express any substring as a just production, as a just sequence of non-terminals, and this sequence will be quite short. Yes, so this sequence will be just will just contain roughly log n nodes. So if there are no runs, this is how it looks like. So for the up layer, this left part, we have for this up layer we have one node on each level at most, and for down layer we have the same. If there are runs, it's not so nice, and there are additional technical details which I don't want to get into, but the situation gets a little bit more complicated. On each level there may be few consecutive nodes on the same level that are selected. But anyway, no matter if there are runs or not, any substring can be explained as a up-down layer, and this up-down layer is always contained in roughly log n nodes, like O of log n nodes on the same level. So we can find this red level with this red nodes on the picture, and this will be our anchor. Yes, one of these nodes one of the topmost nodes of our context insensitive decomposition. We should be able to go locally C log n nodes to the left and C log n nodes to the right, and this will be the word for which our substring is contained in completely. Okay, so that's the idea. Any up-down layers containing log n nodes on the same level, and of course we are able to maintain this parsing efficiently. So any change of letter only incurs log square n insertions or deletions of the nodes and layers. And our goal is, as I said earlier, is to anchor the LCS at one of the topmost nodes of context insensitive decompositions. So we built, as I said in partially dynamic LCS approach, the approach is the same. We still want to maintain some data structure for pairs of strings, this left part and right part from each anchor. We built two compact tries. TP, this left try, will be for left parts, and TQ will be for right parts. Left parts will be written in reverse. So we go from anchor C log n nodes to the left, and we create we add this to our try. The same we do for the right part, but we add this to TQ tree, and we do the same for T. So both S and T are stored in the same try, but the left parts are stored in one try and the right parts are stored in another. but the leaves in our tries are labeled with both the color. The color means the origin of word, either from S or T, and also the label is numeric. This number means what is the position of anchor. Yes, because when we want to choose the left part and the right part, we need to choose the parts that goes from the same anchor. So now we see this heaviest induced ancestor query here. So the goal in our tries is to find the node U and V, for which the total string depth is as large as possible, because this will be the length of our common substring. And these nodes should contain in their subtrees, they should contain a common pair of red leaves. So the same number should be the same position of red anchor and the same position of blue anchor. Yes, so there should be one common red leaf and one common blue leaf. That's the same level. So we create such tries. So we have these candidate pairs, and there's only one node that should, one topmost node that should catch the occurrence in case there are no runs. Yes, and the goal is to maintain the best solution now. So the goal is to find, we have two families of pairs of strings, red part and blue part, depending whether these strings comes from S or from T. And pair of string means like the left part, reversed left part and right part of string coming from anchor. We want to find pair of strings in red family and pair of strings in blue family, for which their LCPs of left parts and LCPs of right parts combined together, the sum of these, their LCPs should be as large as possible, because this will be the length of our common substring. Yes, so that's the idea. As I said, yes, we have this tries for left, for right. We have to find this. We have to solve this HIA problem efficiently. It is possible to solve this problem efficiently. This was solved earlier. So when we want to insert some candidate pair, so when we want to insert something to red or blue family, we get as a parameter, we get the handle from the dynamic collection, this the one from Soda 18 paper. We get the label and we get the color. We for both tries separately, for the tree that stores reversed left parts and right parts, we basically want to solve LCP queries to get the result, to be able to get the LCP. When we want to delete something from there, we only remove label of the leaf. If we care about space, we can rebuild the tree every some time. And on this, we maintain heavy light decomposition. On this compact tries, we maintain heavy light decomposition. Of course, this should be dynamic. This is easy. We can still rebuild the trees, rebuild this decomposition, heavy light decomposition, every some time, whenever needed. And the good thing here is that any route to any node path is decomposed only to log n heavy paths, parts of heavy paths. So for pairs of heavy paths, one heavy path comes from P and one comes from TQ. For a pair of heavy paths, we can maintain additional point structure that stores set of points. And each such structure sends its result to global max heap of candidates, as it was similar to partially dynamic idea. And each point structure stores points, and we are able to insert or delete points, and the goal is to maintain the best result for pair of heavy paths. So we translate the position on heavy path coming from P try, and we maintain the position of the depth in TQ on the heavy path in TQ, we translate it into point in our structure, and we want to be able to find the point, actually pair of points that maximizes these LCPs that we mentioned earlier. So what is good is that any labeled leaf contributes only to log square point structures. So we only keep point structures for that are non-empty. Yes? So we have some hash map of pairs of heavy paths. Inside we have some point structure, and the goal is to find this best bichromatic point, pair of points that gives us the highest LCP total, LCP of left parts and LCP of right parts. And this is simply augmented dynamic 2D range search tree that maintains several information to be able to provide us this best bichromatic pair. The information are computed recursively from its children, and any insert or deletion to a point structure takes log square and time. That would be it. Thank you for listening. Thank you for watching. Hopefully it was useful for you. And bye.